Welcome dear students. Today we are going to discuss about Freidel-Crafts alkylation reaction. Freidel-Crafts alkylation reaction is an example of electrophilic aromatic substitution reaction. So first we will discuss about electrophilic aromatic substitution reaction in short, and then we will discuss about the reaction, that is Freidel-Crafts alkylation reaction, its mechanism and the drawbacks. So first let us see what is electrophilic aromatic substitution reaction. To discuss this, we have to understand the structure of benzene. Benzene has got 3 pi bonds, okay, 3 double bonds are there, so that means it has got the 6 pi electron. Now the beauty of benzene is that the 6 pi electrons are in constant dynamic motion. Okay, so that gives us the second structure of benzene. You can see here the electron pair, it goes here, this electron pair comes here, this electron pair it goes there. So that leads us to 2 structures of benzene. Okay, so the actual structure of benzene is neither structure 1 nor structure 2. It is a combination of both these structures, and such a combination of both these structures is referred to as the resonance hybrid structure of the benzene. So we have represented you can see that the electrons are in rotation. Okay, so we have represented it like this overall. For simplicity we can write it like this. Okay, so now if we are introducing an electrophile into the system, as you can see the electrophile is having a positive charge. It wants to get neutral. So for getting neutral, what it should do? It should take an electron pair. So it can approach the benzene ring for the electron pair, but rather unsuccessfully, because the benzene won't give the electron pair to electrophile. That would mean that the benzene would have to partake from its delocalization and resonance stabilization. So therefore the benzene is not able to give. So electrophile is not being able to get in this manner. So what other alternative the electrophile has? Yes, it can replace or it can substitute one of the hydrogens of the 6 carbon atoms of the benzene ring, and that hydrogen, that dissociated hydrogen, it can go with a base or conjugate base that we use in the reaction system. So from this analysis we understand that benzene undergoes electrophilic aromatic substitution reaction. What it undergoes? Electrophilic aromatic substitution reaction. Freidel-Crafts alkylation reaction is an example of electrophilic aromatic substitution reaction, as already discussed. So what is the electrophile and what is the let us see. In Freidel-Crafts alkylation reaction there is a benzene ring, of course, no doubt, but the electrophile here is CH3 plus. And the product that is formed here is alkyl benzene. Okay, so here it is methyl benzene or toluene. So that is the importance of Freidel-Crafts alkylation reaction. What is the importance? That it is used in the preparation of alkyl benzenes. It is used in preparation of alkyl benzenes. Let us now see what is the reaction. Let us now see the reaction. Absolutely right, there will be a benzene. We use the alkyl halide, and we use a Lewis acid catalyst, FeCl3 or AlCl3. We can use whichever. Here let me use AlCl3, and what we get is, yes, alkyl benzene and HCl. That's it. So the benzene reacts with alkyl halide in the presence of a Lewis acid catalyst to give alkyl benzene. Let us now look at the mechanism. As discussed, that Freidel-Crafts alkylation reaction is an example of electrophilic aromatic substitution reaction. Electrophilic aromatic substitution reaction has 3 steps. Step number 1. Can you recollect who is the problem maker here? Who started the problem? There was no problem in the first place. Who started the problem? Yes, electrophile has started the reaction. It is the problem maker. So electrophile has to be generated from somewhere, right? So we are going to see how the electrophil is getting generated in the first step, that is formation of the electrophil. Formation of electrophil. Let us see how it is getting generated. It is getting generated from CH3Cl, right? Let it react with Lewis acid catalyst. Now, in Lewis acid catalyst, the Al has a distinguishing character. What is it? It is having an empty d orbital which can accept a pair of electron. So it can accept Cl minus into it. Okay, so we get CH3 plus and we get AlCl4 minus. Note that. Okay, this is the Lewis acid and this is its conjugate base. We will use the conjugate base in the third step. Okay, so that's how we get our electrophil. Step number 2. Now the electrophil is generated. Do you think it will sit idle? Does it have a role or does it have a function? Yes, it won't sit idle. It would attack the benzene ring. So step 2 would be the formation of carbocation. Formation of carbocation. So as we said, the problem maker, that is electrophil, is already generated. Now it won't make the benzene to sit in peace. It would attack it. So what would result? Now electrophil wants an electron pair. It can get from this position and this position. So assume that it is trying to get from this position. It is successfully got, and from this here it has got this electron pair from this position. So you get something like this. This carbon already has a hydrogen. I am writing it. Actually all carbon have. I am writing all carbon are having this hydrogen. I am writing for this carbon only for the better understanding of the mechanism. So here it is there. These electron pairs are undisturbed. The electron pair has been donated from this position. Now when electron pair has been donated from this position, this electron pair was made up of 2 electrons. This carbon's electron is still here, while this carbon's electron has gone to CH3. So which carbon is at loss? Absolutely right, this carbon. So this is the first structure. To negate this positive charge, this electron pair shifts here. And you get a second structure like this. This electron pair shifts there, fine. When this electron pair shifts here, this is also made up of 2 electrons. This electron is still there with this carbon, while this electron has gone here. So the loss is with this carbon atom. So the positive charge comes here. Now to negate this positive charge, this electron pair shifts here. And you get a third structure like this. When this electron pair shifts here, this is also made up of 2 electrons. This electron is still with this carbon, while this electron has gone there. So the loss is with this carbon, and therefore the positive charge comes here. So we get 3 structures, 1, 2 and 3. 3 structures for the carbocation. So we can represent the overall like this. The positive sign is just rotating, right? The positive sign is just rotating. It is distributed around the carbon atoms. It is very unstable state. This state is very unstable. Step 2. Let's go to step 3. As you know, unstable state won't remain as such for long. The step 3 is abstraction of proton. Abstraction of proton by base H plus by base. Let's see. So what is our carbocation? Let's redraw our carbocation here. That is positive sign will come here, CH3H, and our what is the base? Yes. What was the conjugate base we used in the step 1? Correct. AlCl4 minus. AlCl4 minus. Now what would happen? It is a conjugate base, right? It can now donate the pair of electron. Okay, conjugate base can donate the pair of electron. What was the Lewis acid? It can accept the pair of electron. Now it can donate. And this system is also very unstable. So this electron pair, it goes back to the ring and this goes here. So now what would happen? What is the product that you get? Absolutely right. Alkyl benzene plus HCl plus AlCl3. Because Cl, one Cl minus has gone there because it has donated. It was a conjugate base. So he has donated a pair of electron here to H plus. So now you get AlCl3 back. So the catalyst is back in the reaction. It has not taken part. Okay. So it is not a part of the reaction. It is back. So this is what is Freidel-Crafts alkylation reaction. Now let us discuss the drawbacks of Freidel-Crafts alkylation reaction. Let us discuss the drawbacks. Drawbacks of Freidel-Crafts alkylation reaction. What is the first drawback? For that, I have to write the reaction once again. Okay, then we will understand what is the first drawback. I will tell you the first drawback, polyalkylation, and then we will understand. Polyalkylation. Let us see what is polyalkylation. So this is the reaction actually of our benzene ring or Freidel-Crafts alkylation reaction. And what was the product that was formed? Yes. Any doubts? Just see. Wasn't this the reaction that we have drawn earlier? Yes, this was the reaction that we have drawn. Now, as you proceed with the reaction, you can see that CH3, what is CH3? It is an electron pumping group, right? It will increase the electron density of the benzene ring. Also, CH3 is an ortho para director. That is, it will increase the electron density at ortho and para position. It will increase the electron density. Now when the electron density increases at ortho and para position, then if next electrophile comes, okay, when next electrophile comes, when CH3Cl reacts with AlCl3, when the next electrophile comes out of this reaction, that is CH3 plus, where would it attack? Okay, whether it will attack this benzene ring or whether it will attack this toluene. Of course it will attack toluene because here the electron density is less, okay, but here the electron density is more because electron pumping group is also there. So electron density has increased at these positions. So it will have a natural preference to attack toluene, right? It won't attack benzene at that pace. So if it attacks toluene, then there can be two possibilities. The possibilities are that this may be formed. This is orthoxylene. Or it can form this also. This also it can form, that is paraxylene. Or one more product can be formed, that would be both, attack at both positions. So what you will get? Yeah, something like this. What is it? 1,2,4 trimethyl benzene. So you can get orthoxylene, paraxylene and 1,2,4 trimethyl benzene. So you can see that you wanted only toluene. Your aim was toluene, but you made all this out of it. So that is the first drawback of Freidel-Crafts alkylation reaction, that is polyalkylation. Okay, let us now look at The second limitation, is that Freidel-Craft alkylation reaction, it cannot take place if a ring deactivator is present in the benzene ring. Let us see with an example. Suppose this is benzene ring and node 2 is present here, and CH3Cl, we are going to do the reaction AlCl3. There will be no reaction at all. Why there won't be any reaction? Because NO2 plus is electron withdrawer. It withdraws the electron. So that makes the electron density in benzene ring to come down. Electron density comes down drastically. So the CH3 plus that comes because of this reaction between AlCl3 and CH3Cl. The CH3 that comes, it doesn't have any kind of attraction towards benzene ring because there is no electron density, as the electron density has drastically come down in the benzene ring because an electron withdrawing group is present or a ring deactivating group is present in the benzene ring. So that is the problem. So that is the second limitation, that Freidel-Craft alkylation reaction won't take place if an electron withdrawing group is linked to the benzene ring, because it decreases the electron density of the benzene ring drastically. Okay, so the electrophile won't feel any attraction towards the benzene ring. Let us now look at the third limitation. Okay, third limitation is vinyl halide and your aryl halides, they don't undergo electrophilic aromatic substitution reaction. What is vinyl halide? This is vinyl halide, that is the halogen atom is linked to carbon which is directly linked to a double bond. That is a vinyl halide. In vinyl halide, carbocation cannot be formed. Okay, aryl halide is ARX. Okay, so these two things can't go Freidel-Craft alkylation. That is, these two things can't attack the benzene ring. That is what it means. Why it can't attack benzene ring? Why these two can't attack the benzene ring? Suppose if X goes from here, okay, so it would come plus, right? So what would be, this electron will jump here, so this charge will go from here, right? So it will become CH minus now, right? So and then it again will jump here, right? Then it will again jump here. So the carbocation is not formed efficiently. There is no electrophile that is formed in vinyl halide. What about aryl halide? Let me draw an arene group. Suppose if X goes with its electron, so positive sign will come here. What will happen? This pi electron, it will negate this positive charge. So the electrophile is not also formed here. So electrophile is not formed in these cases. Therefore, it can't attack the benzene ring. Therefore, that is what we say, vinyl halide and aryl halide won't undergo Freidel-Craft alkylation reaction. What is the fourth drawback? Let us see. The fourth drawback is Freidel-Craft alkylation reaction is only possible for methyl halide as well as ethyl halide. For alkyl halides greater than ethyl groups, it is not possible because skeletal rearrangement takes place. Okay, to demonstrate this, let me give you an example. Okay, suppose this is the benzene ring and CH3, you are using N-propyl halide and you are trying to go for Freidel-Craft alkylation. The product that you get is, you should get, what you are expecting is CH2, CH2, CH3. That is what you expect, right? plus HCl, fine. But this is not that product that you get. This is not the actual product that you get. You get a product like this. This is the product that you get. So you were expecting N-propyl benzene as product, but what you have got is isopropyl benzene. So for higher alkyl halides, you won't get the expected product. So you were expecting N-propyl benzene, but you got isopropyl benzene. Why you got isopropyl benzene? That let me show to you why you got isopropyl benzene. Let me show you the mechanism. First step in this, suppose if you are taking N-propyl halide and you are reacting it with your acid catalyst, Lewis acid catalyst, then you get your electrophil like this. Right? Now this is a primary carbocation. Okay, this is not stable. So what would happen? An H from this position, it will go at this position. Okay, and you get something like this, CH2, sorry, CH3, and the positive sign here, it will come here. This is more stable. Secondary carbocation is more stable. So skeletal rearrangement takes place in the first step. In the formation of carbocation itself, in the step 1 itself, skeletal rearrangement takes place. The primary carbocation that is formed converts itself into secondary carbocation because the secondary carbocation is more stable. Why it is more stable? Because here the positive charge is drastically reduced. Why? Because electron pumping groups are present on the both sides. They pump their electrons and reduce the the positive charge here. So the secondary carbocation has less positive charge. It's more stable. So the secondary carbocation is formed in the first step itself. So this is what will attack the benzene ring in the second step. So this carbon will attack. So you get, in the third step, you get isopropyl benzene. So you don't get the expected product when you use alkyl halides greater than ethyl halide. So these are the drawbacks of Freidel-Crafts alkylation reaction. Dear students, in this video, first we have discussed what is electrophilic aromatic substitution reaction and how electrophil attacks the benzene ring. Then we have discussed the reaction of Freidel-Crafts, then mechanism, and we have discussed the drawbacks also. In drawbacks, we have discussed 4 drawbacks. Number 1, we have discussed about polyalkylation. Second, we have discussed about your that electron, if deactivator is present in the benzene ring, it won't undergo Freidel-Crafts alkylation. We have seen how aryl halides and vinyl halides do not undergo Freidel-Crafts alkylation reaction, and lastly we have seen how it is not how we don't get the expected product if we are using higher alkyl halides. If you like the video, if you have understood the class, please do subscribe. Thank you very much.